Next speaker is Roberto Calandra from UC Berkeley, and Roberto is going to look a little bit more at robotics and is going to talk about goal-driven dynamics learning for model-based reinforcement learning.
Thanks, Mark. Hello, everyone. I'm really excited about this workshop and in general about being here at DALI. I think it's really, really cool. So what I'm going to talk today is some recent work that we did on goal-driven dynamics learning for model-based RL. And just to give you a sort of framework, what I'm essentially interested is controlling complex robotic systems. In the last 15-20 years, we have increasingly complex robots that are in theory capable of solving really a wide range of tasks, but at the same time, designing controllers for actually solving the tasks that we care about is extremely challenging and requires a substantial amount of engineering, typically years, in order to solve even tasks that we consider trivially, like picking objects or navigating environments. And if we look at standard control methods, the sort of all the control methods that are used nowadays rely on the presence of models of our dynamics that tell us how the system is going to behave. Classical models that we care about are the forward dynamics, for example, where given a state and an action, we want to predict what is going to be the state at the next time. And this is true both for most control, let's say traditional control approaches, but also in model-based RL. Now, the problem with the idea of using this dynamics model is that these models are usually trained just with respect to the marginal likelihood, for example, where we say we just want to optimize the error with respect to the next state where we are going. However, these models are used in a control loop, which means that we want to estimate how full trajectories are going to develop. And in the moment where we start predicting concatenations or a series of prediction, what's happened is that the error will compound in a multiplicative way. And this leads to the fact that even very small error in our model will predict or can potentially predict very inaccurately over long distances. So there are many ways that people are at the moment looking for in order to solve this issue. One possibility is the use of models that explicitly consider this time series where you try to predict many steps ahead. Another possibility is the use of uncertainty, which is particularly important in robotics, and approaches like PILCO try to account for uncertainty also over long sequence of steps. And the third possibility is to make use of a stronger supervision. And in this work, we are going to look at how we can make use of a stronger supervision in order to improve our, let's say, dynamics. So if we look at the sort of control diagrams that I'm referring to, what we typically have is that we want to learn a dynamics. From this dynamics, we can then compute some expected reward over the trajectory. And then what we typically want to do is that we want to optimize a controller with respect to this reward that we have. And once we have a policy that we are satisfied, we go in the real world, we try it on our robot, and what we get back is typically a sequence of state, action, and reward that we visited. And out of this, we will take the state and action, and we will essentially feed them back to learn a better dynamics model. And then we will start iterating over. If we look at classical control, it's also very similar. We just don't have this loop here. What happened would be that we just learn the dynamic once, for example, using system identification, and then we go on to optimize the controller only once. However, what we can notice here is that the environment is actually giving us more information than what we are using, because we also are getting the reward. So the question is, how can we incorporate the reward in order to push and guide essentially the whole process to learn better policies eventually. And the important part here, I think there are two important factors. One factor is that in this previous framework, we're actually not making full use of the information that the environment gave us. And the second fact is that also in the traditional framework, we are essentially dividing the problem into two very clear boxes. One boxes that say, okay, we are learning the dynamics model. The second boxes that say, okay, now we optimize it. And in practice, having this artificial separation between what we want sort of force us to have auxiliary rewards about which we don't really care. We don't care about how accurate the dynamics model is. We only care about eventually how good our policy is. And it's sort of silly to optimize one thing, hoping that it will improve a second different criteria. So the overall reasoning is, why don't we directly try to optimize with respect to the reward? And the idea of learning a dynamics model in a goal-oriented manner has already been thought about in the literature, exists, but the main issue is the fact that you need to compute gradients of the dynamics with respect to the reward in order to be able to do some sort of gradient descent over this dynamics. And in practice, computing these gradients analytically, it's usually infeasible in closed form. So you need to approximate them, but this is usually very difficult. So what we propose to do instead is to use a zero-order optimizer, and specifically Bayesian optimization, where we don't need to compute gradients. We only really look at the reward, which is something that we already get from the environment. So just to have an idea, how many people are familiar with Bayesian optimization? Okay, so a good percentage. I will very quickly go through. The main idea of Bayesian optimization, or the sort of problem that Bayesian optimization is usually used for, are non-convex, or in general, any sort of objective function which can be convex or non-convex. It can deal with stochastic noise, which is very nice. It's a zero order, so we don't need to use derivatives. And it's usually applicable or most used in applications where you want to have very few number of samples in order to converge. Because you don't probably want to run Bayesian optimization for millions of evaluations, but perhaps hundreds or thousands. And the main intuition behind Bayesian optimization is that we can essentially use all the previous evaluations that we have, so the couples of parameters and reward, in order to create a model, typically a Gaussian process. And once we have this model, we can essentially run a virtual optimization over this model. And then only once we have the optimal parameters, we go in the real world and we try them on the real system. And then we can update our model and start again. So just to give you a very brief example, imagine that you have initial underlying function, unknown function, which is the blue one, and you want to optimize it. Initially, your model will be not very informative. We'll just say, oh, I essentially don't know, because I only have one data point. But every time that we collect new data, the model will get a little bit more accurate, until at some point we will have models which are realistically good, at least locally, with respect to the minima, and then the optimization is essentially done. And as you can see, the parameters that we can select essentially can jump around, don't need to be, let's say, restricted to a local minimum. So the sort of control framework that I will give you now is the one that we use at this stage, and is sort of the base of all the experiment that we do. And this is essentially the linear quadratic regulator. The idea is that you have a linear dynamics model, very simple, and what you want to do is you want to learn a controller, for example, again, a linear time invariant controller, which only depends from the state where you are. And what you want to do is that you want to ideally optimize this cost, which again depends only from the state and the actions that you have in this particular form. And the nice part about the linear quadratic regulator is that they are very widely used in the real world and are very well known, and they have an analytical solution. So we can compare against an analytical optimal solution, which is nice, even though it's not near to real world, let's say. And the main intuition about the work that I'm presenting here is that even if we have nonlinear dynamics, we can actually find linear dynamics which are somewhat very close to being optimal, for example, by linearizing around the trajectory that we care, so that we only want to be precise in the area that we care. We don't need to be globally accurate. And the overall control schema, the overall flow of our approach is this one, where we have a linear dynamics. We compute a controller by optimizing the cost function, for example, in closed form. And then we go into the actual system, we try it out, we compute the reward, and using Bayesian optimization, we compute the next linear system. And in particular, what we are doing here is that we are optimizing these A and B matrices. And so we started by looking at a series of standard benchmark and toy problems that exist in the control literature and in reinforcement learning literature. And the first question that we wanted to answer was, can we solve nonlinear tasks using a linear dynamics and by computing the controller using LQR? And the answer is yes. We can compute fairly good solutions in a reasonable amount of iterations. So in this particular problem, we can go below 5% from the optimal solution in below 800 evaluations on the real system. This is the case where we just use the cost specified here, and if we actually use the log of the cost, then the performance increases even further because the model is a little bit more accurate. So in this case, we are about 2% from the optimal control. This is very good for a real system in real world. So the answer is yes. If we look at also at the state and action, we can see that the one that we are learning are very close to the optimal ones that we would get from the real system, from solving analytically the real system. However, are we really learning the true dynamics? And the answer is actually no. So if we look at the cost function, what's happened is that the really important part is the ratio between the parameters that you are learning. So effectively, while the real parameters is here, the one that is learned, it's far away. However, if we just look at the cost function, it's virtually impossible to distinguish between these 2 points because they both achieve extremely good performance. So what we are effectively learning is something that doesn't have or does not necessarily have a physical meaning in terms of dynamics, but still it's very useful for solving the task that we care about. And another nice properties of this model is that we are not restricted to using LQR system for actually computing the controller. We can also use more complex solvers like MPC, and even in that case, we obtain fairly good performance. A little bit worse than in the LQR case, but still fairly good. Now, we also compared to a number of approaches that exist in the literature, both in classical control. One of these is the idea of tuning the cost Q and R. This is it's a very interesting idea that has been already used for many years in classical control, and this is actually equivalent to what people have been rediscovering in reinforcement learning. It's the idea of dynamic reward shaping, where the idea is that you have a dynamics model which it's wrong, But by playing around with the reward shaping, you can actually force the system to converge to a good solution. And we directly compare using Bayesian optimization, and what we can see is that while this approach of dynamic reward shaping work well in the presence of, in absence of noise, so the dashed lines are it's learning the Q and R, and the full lines are instead it's our approach. So in absence of noise, their approach work better. However, in the moment where we start having noise into the system, the performance of this dynamic reward shaping degrades really, really quickly, while our approach seems to be fairly robust to noise. So the black case is with 10% noise, and the blue case is 20% noise. And you can see that even with 20% noise, after about 200 iterations, we still find the optimum, or something that is very close to the optimum, while the other approach degenerates. Another possibility is instead would be to do direct policy search, where we would directly optimizing the parameters of the controller. And in this case, this is equivalent would be equivalent to learning the gains of the linear controller directly. In this case, what turns out is that if the cost that we use is very simple, for example, quadratic, learning directly the policy might turn out to be a good idea because it's faster because the number of parameters is smaller. However, in the moment where you have quadratic costs that are not quadratic, that are more complex, it's actually much harder problem because the optimizer will need to do a substantial amount of heavy lifting in order to learn this function. So this was also very interesting. And finally, we compared to the classical system identification plus LQR, where we separately learn the dynamics at once, and then we essentially optimize the controller. And even in this case, what we see is that we have essentially one order of magnitude better performance by learning the dynamics online rather than doing system identification with the same amount of data. So overall, okay, let me show then. We also went to in the real world, and we actually tried on a quadcopter. So this is the Crazy Fly. It's a very small quadcopter, and what we wanted to check if we can use it to track very simple trajectories. So keep in mind that it's still a proof of concept. It's not a very complicated task, but oops. So what we do is that we have a mock-up system, and we say, okay, starting from point A, just go to point B. Very simple. And what turns out is that our approach is about, after 50 experiments, is about 10% better than classical control methods, where you identify the dynamics, and then you learn a controller over this. On a real system, and using a dynamics that has been extensively studied, which is the one of the quadcopters. So we were fairly happy about this, but I think that the part that was really interesting was to actually compare all of these approaches, because it's not obvious at least initially, it was not obvious to us in which case doing one or another strategy was better, in which case we should optimize, for example, the Q and R, or when we should optimize F, or if we can optimize the dynamics. And it turns out that the idea of optimizing the dynamics is actually fairly reasonable, and there are many cases where it's in practice useful. So this work has been done in practice mostly by, all the real experiment has been done by Somil and Ted, which are the collaborators. And also the other people that collaborated are Claire and Sergey, more on the theoretical side. And this paper, this talk is mostly based on this archive paper that we put up a couple of months ago. So to sort of summarize and conclude, I like very much this citation from George Box that all models are wrong, but some are useful. And I think that this is particularly true in the case of robotics. So not necessarily learning dynamics model in the traditional way is useful. It's highly desirable. It's what we would all like to do, because then it means that we can transfer this dynamics model from one task to another. But this approach would also require to have essentially an infinite amount of accuracy in our models. So in practice, in the real world, this is not always feasible, because even small error can lead to suboptimal policies. So what the sort of question that we wanted to answer today is, are accurate dynamics models really necessary to solve the task that we care about? And the experimental results that we get show that it's actually not always necessary. We can get away by having dynamics models that are inaccurate, but are useful because they are accurate, or they might be accurate in the right place, or they might just be useful by being inaccurate. And in future, we want to extend this work to essentially, first of all, include more complex settings where we have nonlinear dynamics, more powerful control schema, and more complex robot tasks. Ideally manipulation and presence of contacts where just classical dynamics model fail heavily. But something that we are also very interested in is to try to combine model-based and goal-driven learning in a more tight way. Because I have the feeling that there is a lot of structure there that current model-based approaches are not exploiting, and same-wise, if you only look at policy search approaches, they also don't use the full information that are available. So thank you for your time, and I'm happy to answer any question.
I really like the way that you phrase it in terms of saying that, well, it's the reward that's important, and the whole construct of the state space in a way doesn't really matter. If you could learn to get good reward, then so to hell with the rest, right? But the problem is that in a lot of cases the reward signal is extremely weak. Yeah. Right? So for example, if you're learning to play a game, well, the only reward signal is either you win or you lose in the end, right? But if you don't have a notion of what's going on in the game, then you can't do that. I think it's very important to try and figure out how would we design experiment? Like what are the consequences for active learning? Just getting a better dynamical model is clearly beside the point, right? It has to be that you get a better model that will enable you to get more reward, right? And so I think focusing on the reward, I'm not sure exactly how to make the trade-off. I think the state space representation is necessary to be able to understand how you can get better reward, right? But it's certainly not the goal in its own right.
Yes, absolutely. So I think that I've been thinking a lot. So, as a control theory, as a robotician, the use of dynamics is crucial. It's at the core of everything we do. And I think it's very reasonable, because also as a human, we do plan, we have an intuition of what's going to happen. But I do think that it's important because it's useful. So it's consequential to actually solving the task. And in some cases, there might be other alternative representations that might equally be useful. And the real question is when. Like, I don't have an understanding of in which cases one representation is better than another, what are the possible representations, and eventually, absolutely, as you said, what we care is about reward. So just learning better dynamics model, if it doesn't help us for the task, that's not useful. It's exercise in futility.
Okay, if there are no more questions, I suggest we have a coffee break. Thank you, Roberto, again for coming.